Okay, now why is it important? Now see, what are the things that we have established? We used linear strain theory, linear bending theory, and we established the relationship between curvature and strain, and then we established the relationship between the curvature and the applied bending moment. Okay. So now let's see how do we do the analysis at transfer and service. So we are going to study in the next class how you do the section analysis to establish this moment versus curvature behavior. So if you do that for a pre-stress concrete system, you will have something called initial curvature. This is an initial curvature. Okay, which will be negative because of the pre-stress you apply, the beam is going to have a camber. Okay, typically it will bend upward, right, for a simply supported case when you apply pre-stress. So that is, this is initial curvature for the cross section, and then your cracking load is going to be cracking load or cracking moment is going to be much higher compared to that of a reinforced concrete member. This is what we discussed in the first part of the lecture in the module 1, that due to pre-stressing your cracking load and cracking moment will increase significantly. So you will find that this is nothing but your elastic regime or uncracked regime. Okay. So most of the time in pre-stress systems we will make sure that your service loads are going to be within or less than the cracking moment or cracking load. So the system will be uncracked. That's the whole purpose of pre-stress, because once it cracks, your moment of inertia will reduce, and we want to maximize the use of your moment of inertia, and you will get maximum moment of inertia only when the section is uncracked. So that is the reason in pre-stress we always make sure that the section is not going to be cracked. So we design it, or even we will study in design. We have 3 types of design: type 1, type 2 and type 3. Even in type 3 we allow little bit of cracking only, but we make sure that the strains and due to crack everything is well within the acceptable limit. So yeah, so if you are in this elastic regime, now how do we do the analysis is the question. In the next module or next lecture, we will see how to establish this moment curvature for a particular pre-stress concrete section. But you can see that the difference between M cracking and let's say this is your M yield, and this is your, let's say this maybe this is M ultimate. You see M yield and M cracking, they are very close to each other. Similarly, M cracking and M ultimate is not really that different. Or in other words, the ratio of M cracking to M ultimate will be getting very close to that of your ultimate. So typically M cracking by M ultimate will be from 0.8 to 1 or so. In design we make sure we do like that. So that means in RC it will be different. The cracking moment will be much lower than the ultimate, but in pre-stress, because we are doing pre-stressing and we are putting the system in compression, the load at which it is going to crack is going to be higher. So the ratio of M cracking to M ultimate will be in the range of 0.8 to 1. That again depends upon how much pre-stress that you do, what are the type of concrete that we use, all those things. But in general, it will be very close to that of ultimate. Okay. So we can say that the moment versus curvature relationship is almost linear till yielding of steel. So yielding, I said somewhere here it is happening, right? So you see here, nearly close to yield, it's pretty much remain linear. The moment at yield also will be slightly lower than the ultimate moment that we said, hence the behavior is practically linear for most range of the moment like we discussed previously. So if the calculated moment for a particular load on the beam is based on the elastic analysis, if you see that, we make sure that the moment demand when we design it in such a way that it's pretty much it is going to be less than the cracking load, or we will make sure that the pre-stress concrete sections are not going to be cracked under service loads. So, the superposition of the load cases is applied to find out the moment demand under combined loads. You see here, in this way, when you do elastic analysis, actually for structural analysis, typically in design, we do linear elastic analysis, we estimate the demand. And when we do the ultimate strength calculations, we actually do inelastic analysis by assuming that stresses and strains are going to exceed the elastic limit. In that way, in a way that capacities will be calculated in a conservative way. When you do elastic analysis, the demands will be estimated slightly in a conservative way. In both ways, demand is estimated in a conservative way, capacities are slightly underestimated. In that way, you get overall better factor of safety in your design. Anyway, now let's look at the concepts of analysis. First, we will talk about stress concept of analysis, right? So, we are going to have three concepts. So, one is a stress concept. The second one is the force concept. The third one is the load balancing concept. So, which we are going to talk about these three concepts. Now, let us say that I am taking this particular, let us say, section. I have drawn it slightly in a way in an elevation view so that you can appreciate. Okay, so this is the section, let us say, and it is subjected to some M external, let us say M external moment that is coming from external load. In addition to that, you have a pre-stress force, which is P, acting at a distance of V from the CG of the concrete section, and your extreme fibers are from the new to CG is, you know, the YT, which is the distance of the fiber at the for the top fiber, and YB is the distance of the fiber, bottom fiber, from the CG of the cross section. Now, we know that what are the different types of load. So, if you see this particular load is moved to the middle, you will find that you have this P. In addition to that, you also have moment due to pre-stress MP, right? And so, these are the things. So, you have load from concentric pre-stress, okay, because we have moved that, converted into an equivalent load. Now, P is at the middle. In addition to that, the equivalent load MP, which is nothing but P into E, right. So, that is from here. So, we have taken compression to be negative and tension to be positive, right. So, these are the sign conventions. So, what are the stresses that are going to come from the applied axial compression? You see, please also note that we are looking at what is the effect of steel on the concrete. Steel, pre-stressing steel, we are stretching it. When you stretch it, it is always going to be in tension, but because it is in equilibrium with the concrete at that section, they are all connected together, right. So, it is going to impose, because the steel, when it is stretched, it wants to come back. So, in that process, it is going to apply compression on the concrete. So, concrete will be subjected to this P and a moment due to pre-stress if it is at a distance E compared to the CGC, right. So, you are going to have concentric pre-stress, which is negative P by A, which is the stress distribution, and then this will be the due to MP, which we said due to pre-stress, right. Now, P into E is the moment, and we know the stress at the top fiber is going to be moment into distance of the fiber divided by the moment of inertia. Again, now pre-stress is applied like this, right. So, it is going to create positive stresses at the top and negative stresses at the, this is completely negative. Now, next effect will be the external load. So, let us say this is M external, moment coming from external load, right. So, that is basically, if it is a simply supported case, for example, that is going to create compression at the top and tension at the bottom. So, this is going to be negative and this is going to be positive, right. So, now we are going to add all the effects. The net stress at the top, you see here, this is going to be minus P by A, then you are going to have plus here P into E into YT by I, then here you have negative mx into YT by I. So, you add all of them. Here I am assuming that everything is going to be in compression. That is what our intention is. We want concrete to be in compression under service loads. We do not want the stress typically at the bottom to be reaching tension, or due to pre-stress sometimes if the external loads are not there, top fiber also can get into tension before the external loads are acting on the member. That also we have to be careful. If you remember in the module 1 we talked about, if you apply too much pre-stress before external loads are applied, then you will have cracking at the top for a simply supported member, right. So, we need to be careful. Too much pre-stress is also not good. So, we need to be careful. So, resultant stress can be written as minus P by A. This is always going to be in compression. Now, depending upon where this Y is, whether it is above the neutral axis or below the neutral axis, it will be plus or minus, and similarly the M into the load effect also. So, this is the, in simplified we can write plus or minus plus or minus. You can use the same formula for any fiber distance depending upon whether it is in compression or tension. Right. Now, using this, let us calculate what is the cracking moment, right. So, pre-stress sections are actually we do pre-stressing so that we can span the member for a long distances. We want large column free space. So, quickly by the amount of pre-stress and the that is applied, we can quickly calculate mere cracking moment. Now, we know that cracking is calculated from tensile strength of the concrete in flexure, which is also denoted as modulus of rupture, FCR. FCR is, code gives you a simplified equation which is 0.7 into square root of FCK, where FCK is your characteristic strength. And for this section, now we are applying a load at which it is going to crack. So, let us say that I am applying a moment of M cracking, that is what I am interested in calculating for a section that is subjected to a pre-stress force at a distance of eccentricity E, right. Now, this because of this should create a resultant stress in such a way that the stress at the bottom FB should reach FCR, FB should be equal to FCR. That is what we are trying to calculate now. Now, let us see how do we do that. Now, because of the effective, so why we have written P is it is effective pre-stress, sometimes you will have losses also, right. So, that is the reason here you have taken as PE, which is called as effective pre-stress that is acting in the section. Effective pre-stress after considering some losses at the service condition when we are doing the analysis, right. And this is now we are calculating the stress at the bottom, right. So, like we explained, there is going to be 3 cases. One is the concentric stress that is coming from equivalent pre-stress that I put it at the CG, which is going to be negative PE by A, which is negative means compression. This is going to be compression. And the next case pre-stressing now is at the bottom. The P is at the bottom means at the bottom it is going to create compression. So, again this is negative. PE into E is the MP pre-stressing moment, and I is the moment of inertia, and Y is the distance of the fiber, which is YB. Now, we are calculating the stress at the bottom fiber. So, again I am assuming everything to be for a simply supported condition, right. So, that is the reason we are saying that at bottom I am going to have cracking. Now, if you are looking at a for a cantilever case, right, then you have to worry about what is happening at the top. So, here most of the examples we are going to deal with the scenario calculation for a simply supported case to illustrate the concept. Now, depending upon the support conditions and your geometry, of course, you have to use your sign convention and see where the moment will be acting, whether it is a hogging moment or sagging moment. Accordingly, we have to design the section, right. Now, we are calculating this MCR. So, that is going to act as an external load or the load at which or the moment for the applied load at which it is going to crack. So, M cracking is the what we are calculating, M cracking into I by YB, and this is going to create tension, right. So, that is why we have written plus here. So, this is going to create compression. So, compression, compression, tension. And now, FCR is given to you, which is equal to 0.7 square root of FCK for a given grade of concrete. We can calculate that, and you plug all these values, and then you get expression for your MCR in a very simple way like this. So if you know the section properties, if you know the amount of pre-stressing, and if you know where the pre-stressing is acting, then using this we can calculate how much a particular section will be able to resist until cracking. Okay. Now let us see. When we do the analysis, this is your stress method of analysis. Now we can also you do the analysis using force method or C-line method. So before that, let us understand how the internal forces and resistance are changing under service loads between a reinforced concrete section and a pre-stress section. So let us look at it. Now if you look at this in a reinforced concrete under service loads, I told you my M cracking will be roughly 15 to maybe about 0.3 of M ultimate, okay, in reinforced concrete. Again, that range why it is coming is it depends upon the tensile in the concrete section modulus that what you have, the cracking moment will change, right. So the cracking moment is very, very low compared to that of ultimate resistance in case of a reinforced concrete system. And we know that service loads are typically service loads, M service. When we design, M service will be roughly 0.6 to 0.7 of your M ultimate. That is the way we design. So if you see that in RC sections, usually under service loads you are allowed to have crack, because my cracking moment is only 15 to 30% for ultimate, but service moments are going to be 60 to 70% for ultimate. So my cracking moment, the sections are always assumed to have cracks, but only in design what we do is we put enough amount of steel in such a way that the crack widths are going to be kept less than 0.2 millimeter or 0.1 millimeter or 0.3 millimeter depending upon the exposure condition. So that is what we do. Now let us look at the cross section or I should say a free body diagram of a, let us say, simply supported reinforced concrete member that is subjected to uniformly distributed load like this. We have two scenarios, which is let us say low loads and this is high load, or in other words we say that W2 is going to be greater than W1. Now what you see here is there is going to be a bending moment that it is acting, bending moment that has to be resisted by the internal forces that are developed in the cross section. Now let us say that the steel is going to be T1 and C1. Now this moment should be equal to, the moment should be equal to T1 into Z1 or equal to C1 into Z1 with the condition that T1 should be equal to C1. Because this is from equilibrium, this is again from moment resistance. So this moment should be equal to the applied couple. So in reinforced concrete, C1 T1 will be equal to same when your there is no axial force, right. When the load becomes higher, when W2, what is happening is, now this is let us say M1, okay. Now in this case it is going to become M2, right. Now for M2 you will find that your resistance again will come from C2 into Z2, which should be equal to T2 into Z2. But however, when you look at it, the lever arm is not going to be changed much, or in other words, in the higher loads the lever arm what it is required, Z2 will be nearly same as that of Z1 in a reinforced concrete under service loads. Then for increased moment M2, then how will I get my moment resistance? The forces have to increase. So moment resistance I can get it from either increase in force or increase in lever arm. In a reinforced concrete, the lever arms do not change much because it is already cracked, and the moment resistance for the service load moments that are applied you get from increase in your internal forces, right. Now let us look at, this is with respect to reinforced concrete. Now let us look at what happens with pre-stressed concrete, right. Same scenario, I am going to take now a pre-stressed concrete member, and we see that at load W1, now T1 and C1 are the internal forces. Now please note that pre-stress systems are not going to be cracked under service loads. Even for a type 3 member, if it is cracked also, the crack width is going to be so small, right? Because then only you get the best advantage in terms of your moment of inertia, so that you get higher flexural rigidity, right? And so then for this M1, now I need to get the resistance M1, right? So M1 in this case again is going to be C1 into Z1 is equal to T1 into Z1, and C1 should be equal to T1 from equilibrium conditions, right? So then how do I get? So this is a state of SS. In fact, when there is no external loads are acting, when the self height is 0, in fact C will be at the level of T. C will keep moving away from T under service loads with increase in loads. Now, when I increase the load to W2, which is greater than W1, now you will find that C2 is going to keep moving up. So that means the lever arm is going to increase, but you will, because the initial stretching itself, we have seen that your initial stretching itself 0.75 times FPK. This is your initial stress that we talked about, right? So FPK is your 1860 megapascal, so FPI will be 75% of your FPK, right? So that is, so initial force itself I have kept so much. So under service loads, the forces, the system is also not cracked. So unless it is cracked, you are not going to have big significant increase in your stretching force, right? So in that way, the moment resistance has to come because the internal forces have to move away from each other. That's how you generate your moment resistance under service loads under less cracking or no cracking conditions. So you will find that the internal forces in two stages, C2 and C1 or T2 and T1 will be nearly same, but I get moment resistance by change in your lever arm. In reinforced concrete, lever arm doesn't change much, but in pre-stress concrete, internal forces doesn't change, but the lever arm changes quite a bit. Okay, this is a very fundamental concept which we have to keep in mind, and this is what we are going to use in force method or C-line method of analysis, because the system is uncracked. Now moment resistance will come from the movement of your compression force, because T is going to be at the location of your strand only. So that's not going to change. So C is going to keep moving away from your T to offer the moment resistance. Now let's look at it. This is what we said. Okay. At transfer, when you look at it, pre-stress, C is located close to T. The couple of C and T balance only the self height at transfer, because transfer, when you transfer the pre-stress, typically there is no external load. It is only the self height of the member that we need to consider in our analysis, right? And we have seen that C is shifting up and the lever arm gets larger. The variation of C and T is not really appreciable. So this is a very important concept we do. That is what we call that as a C-line method or a force method, okay, of analysis. Okay. So moment is C into Z or T into Z. So somehow I have to find where the C is acting. So we say that the tension force is not really going to change much. So it's one way, it is the the same thing what we did in stress analysis only we are considering, okay. And pre-stressing force is actually considered as an external compression force, because C is always equal to T. You know what is the T that you have applied, so you can assume that the system is going to be elastic and just apply C wherever you want, in the sense for the applied required applied moment. Then you do the analysis. So now let's see how do we do that, right? So right from beginning, that means your initial force T is given to you, which is, let's say, 0.75 times FEK into AP. Okay, so this is the tension force that is given to you, right? And we have seen that T is not going to change whether in the service load domain. Once the system crack gets to yield, then it will change. But we are saying that under service loads, the magnitude of C and T is not going to change, right? Now let's see. We are assuming that C, the moment resistance comes like this, and then now we need to see where at E prime, at what distance this compression force is going to act. Now what is E prime? You have seen that the total lever arm Z is nothing but E plus E prime. Now what is E? E is your eccentricity of the cable, and E prime is the distance at which the C is acting. If E prime, let us say that above the neutral axis it is positive, below the neutral axis it is negative. So, typically under service load C will quickly move and it will go above the neutral axis. So, we are saying that what is the E prime. So, that means E prime is nothing but Z minus C. Now, the question is how do you calculate your Z? So, the Z or Z is the lever arm. So, for that we know what is the moment that is acting on the section. Moment acting on the section, if it is given, if you say that you have done the preliminary design, you know what is the length and you know what is the expected load, then for that span and for that loading you can calculate from your analysis what is the moment acting in the section. So, once the moment is given and we also know what is T, which is basically 0.75 times let us say FPK into AP. So, once moment and T is known to you, I can quickly calculate my lever arm. Lever arm is nothing but moment divided by the tension force, which will give me the lever arm. Once I know the lever arm, in a way I can find out where the C should be, so that it will satisfy the applied moment. So, E prime can be calculated from the calculated lever arm and the eccentricity. Eccentricity will be typically will be assumed. So, you know what are the level of, for once a cross section dimensions are fixed, we know what is the maximum eccentricity that is possible in a cross section. So, E prime is nothing but m by T into minus E, right. So, if you substitute that, now you see you are assuming only C is acting in the cross section. That means C is going to be applied at an eccentricity of E prime. So, that is going to create a concentric compression stress of minus C by AC, and now C is at a distance of E prime. So, the moment due to the C is going to be C into E prime. So, this is a moment due to C that is acting at a distance E prime. Now, we are let us say we are calculating stress at the top. So, CT is nothing but your distance of the fiber at the top, and IC is nothing but your moment of inertia of your cross section. Similarly, I can calculate. Now, you can write that as YT also, because last section we use distance of fibers are either typically noted as C or Y. You can take this as YT. So, now for example, this is your YT and this is your YB. Okay. Right. So, again stress at the bottom, C by AC, again compression. Now, this will become tension because now C is at the top, bottom it is going to create tension. So, that is why plus. So, in this way, but only thing is we are doing the analysis by assuming only C is acting, and C is always given to you once you know what is the pre-stressing force that you apply, that is given to you. And if you know the moment that is acting in the cross section, then you can quickly calculate your lever arm. From the lever arm, you can calculate how much should be the eccentricity of the compression force. We assume that the C is going to act as an external force at a distance EC, and we simply calculate the stresses only with C. So, that is your force method or C line method of analysis. So, again C is equal to T equal to P, this equilibrium always has to be satisfied. Again T is just assuming, here assuming no losses. Okay. If losses are there, of course, we have to account for that. Okay. This is assuming that no losses are there, right. Because jacking stress is always 75% of your characteristic strength.